tensor. Basically, because we already established that the electric potential phi and A form this what we call the potential four vector, right? Included. Okay, yeah. And so this is a covariant vector, and the covariant field tensor is defined by just the derivative of the gradient of this potential for vector, but define it in the anti-symmetric way. So this operation and then reverse the order. Okay. And at first, it didn't look like anything related to the field, but we show by just considering term by term, because this is the gradient and then the time derivative of A add up to the electric field and so on. So that in matrix form is this one, so 0. All diagonal elements are 0 because of this one is anti-symmetric, so that's quite obvious. And then because of anti-symmetry, you only have 6 elements that are independent. The other 6 are the negative of the corresponding one. So this is minus EX. This would be EX. Right? And by the way, now in these two sections, Jackson go back to X, Y, Z. 0, 1, 2, 3 is represent the time, and X, Y, Z. That has changed. Previously, this one is Z, but now in this section is going back to X, Y, Z. So just to be a little careful, because X is the direction that you have the relative velocity. Later on, we'll develop the relative frame is along X direction. That's how we write down the Lorentz transformation. And then the magnetic elements is slightly less easy to memorize. So this is XY, that is Z. This is minus, this is B, actually BY and minus X. Correspondingly, anti-symmetry minus BY. Okay, so we fit the two field, electric field, magnetic field with 6 elements totally. Fit all these 6 independent elements in this second rank anti-symmetric tensor. So that's kind of nice, but we still need to write the Maxwell equation in the form of the this tensor. We skip a little bit first before we go to the two Maxwell equation with source first. So the two divergence E is, this is in Gaussian. I mentioned Jackson make this change back to Gaussian in this section with good reason, because now in Gaussian, all the elements you don't have are the same as the electric field, magnetic field. So they are all of the same dimension. If you go back to SI, then the B will also will all change to B times the speed of light. But many people doing special relativity in general, we set the speed of light equals to 1 anyway. So that will take care of that, even if you use SI unit, but with C equals to 1. Okay, so that's the Gauss law, and then the other one is the Ampere's law. This is microscopic, obviously. And obviously, we already mentioned that the right-hand side, we have another 4 vectors. J is the C times charge density and current density. This is also a four vector, so you can say that if you divide it by C multiplied by C, so the right-hand side is the same. The elements of this four vector, the charge and current density four vector. Okay, and now you want to write these two equations, combine that using this field tensor, and at first it doesn't look like looks like easy, but I mean you go to this and try to figure that out. That seems like a little bit difficult at first, but once you recognize that this is just basically this one with the constant 4 pi over c, you know the right hand side. Now the left hand side will be some kind of derivative because this is divergence derivative. You have ddt, which is the zero element of the gradient four vector, right? We have this gradient four vector, but we define gradient four vector two differently. So one is the covariant, one is the countervariant, the other is covariant. But we remember the covariant one. Actually, we define it using the derivative of the countervariant space-time four vector component. So what is end up is let's see here. The derivative here actually positive rather than negative, right? The covariant, we just use a four vector. This is contrariant. You change the covariant, changes the negative sign, but not the gradient. The gradient one, yes, you have a positive sign. So you need to be a little careful about that. Okay, so that looks like the left-hand side has all these elements. You have ddt, which is a zero element, and you have all these gradient. You have divergence and curl, both are components of the gradient. So that suggests that we can, the right-hand side would be the gradient of this field vector, a field tensor, and the right-hand side is this current density four vector, which is just a four vector. So to get a four vector out of a four tensor, you need to get rid of one of the index. And one way to get the index is what we call the contraction. You contract a subscript with a superscript. So you have a superscript, you contract it with this gradient four vector, like a function of alpha beta. Contraction means a sum over alpha. And the right-hand side supposedly would be this one. So that's just a suggestion, but we need to see whether this that actually true. This is corresponding with this by simply checking it. So it's a component by component checking it whether it's true or not. Okay, so that's one way to hopefully this learn for all these derivation is that you remember whenever you have this very abstract notation, including for this index notation, four vector, four tensor. So in order to do explicit thing, you just keep moving. Don't panic. Just doing component by component. Check everything one at a time, and finally you get it. Okay, so that's part of the reason going through all this derivation. So now to check that, we did one at a time. Say I should say this is J, not this J beta. Okay. You contract this. This would be J beta. This should be 11.141. Okay. Let's check the beta. If beta is 0, which is this one, C times rho, and so we sum over alpha. So alpha can be 0, 1, 2, 3. So you have to check. So basically 0 F 0. If beta is 0, beta 0, right? We check whether this is true, and plus also 1 F 1 0 plus 2 F 2 0. partial 3f g0. Right, this is just that, just write out explicitly. And the reason is that now we substitute the corresponding elements. So partial 0 is this one. So partial t. C. Actually, if you are familiar with this, you already know that F00 is just 0 for the. I'll write it out explicitly so you know that the process is just substitute all the corresponding element from these 4 vector 4 tensor and just going through all the details, and then you see that finally you get what you want. So that's F00 is 0. Now for this one, F1 is just partial x. According to this convention, 0, 1, 2, 3 is t x y z partial x, and F10 is this one. 10 is ex. This is 0, 0, 0, 1. This is 1, 0, 1, 1, and so on. So 1, 0 is ex. Okay, and then plus partial 2 is partial y. 2, 0 is ey, and then partial z. 3, 0 is ez. Okay, so these 4 add up to be just this one, which is just this equals to that, this equals to that, this equals to that. This is just our divergence. Okay. Right? You see that? Right? And the right hand side, now you check where the right hand side is. This 4 pi over c and j. This is 0. So j 0 is c times rho. C times rho cancel rho with 4 pi. Rho. Okay, so the first element, we check that. The right hand is the first element of the right hand side of this equation. This is the equation we want to check. Okay, 0 is done. Okay, now the next one is 1. 1 is, according to this, is j sub x, the x component of the current density. Now we're writing this partial. Do it again. So partial 0. F. Now it's 0, 1. That's partial 1. F1, 1. Which is 0. Now we know that with the anti-symmetric. So U F2, 1. That's partial 3. F3, 1. So this is the one component of this one. You sum over all the. Okay. Now substitute things. So this is again. This is partial t c into the denominator. CO1 is 0, 0, 0, 1 is minus e sub x. And this is partial x, y, so partial y. F2, 1, 0, 1, 2, 2, 0, 1, 2, 1 is e sub c. Okay, so that's this one, and this one, partial z. F3, 1, 3, 3, 0, 1 minus b sub 1. Okay, and now you see whether that is so this is partial bc partial y minus partial by partial c. You know, this is the x component of the curl of b. Okay, so this is this equals that is equals to minus c partial e sub x partial t plus curl of b in the x component. Okay, now we see whether that is equals to, so this is just this one, the x component of this one, right? X component is you have the ex here, partial t, 1 over c, and x component of curl b. So that's the right hand side of this one, right? And the left hand side of the right hand side of this one is J1. J1 is just J. I mean, the 4 vector J1, J superscript 1 is this the X component of current density. Okay, so that check. All right, it's okay. So, and I won't do that. The other two will be similar. So you can convince yourself that the other two is just following the exact same way. And you check that you can write the two Maxwell equation with source. The right hand side is non-zero, and into this form. This form is the gradient, the subtraction of the gradient for vector with the 4 tensor, field 4 tensor. Right hand side with this constant multiplied by current density for vector. Okay, so we got this done. Take care of two Maxwell equations, right, and write it as a single equation in tensor notation. So that kind of need the form is actually need less complex than this one. If you remember all the derivation, of course, you remember how you define the field tensor. Now you write the Maxwell equation in a nicer form and reduce the number instead of two equations. Actually, this is with 4 components, right? Because this is what we call a scalar, it's just one quantity. This is a vector equation, so you have 3 components, so totally 4 components. You combine all that in one single equation, which is also 4 components because you contract this alpha, so beta going from 4 of the beta. So also 4 components, but at least in a more compact. Okay, so we got 2 of them done. Now the other 2 Maxwell equations are without source. Basically, is the right hand side is 0. So basically, write down is divergence B is 0, right? And then the other 2 equations, the other vector equation is the Faraday's law is curl E. Now it's plus 1 over C positive B positive T equals to 0. Okay, so you have 2 more. Okay, and to write it out, it turns out that you need to introduce other objects rather than using this one. I mean, in principle, you can write it, but it will bring a much more complicated expression. Instead of doing that, we define new objects so that the equation looks nicer. Okay, and first you recognize that these 2 set of equations are similar, right? That's the corresponding to it. First of all, you just set the right hand side to 0, so that's okay. The other is the similarity is that if you change E from this set of equation to B, E change to B, right? Then you get this equation. But for this, if you change E to B, then you're missing this sign because this is B, this is minus, this is plus. So when you change B to E, then you need to introduce a negative sign. So basically, you need the B change to negative, E change to B, B change to negative E. Then you can get this to this one. Okay, so this is just basically from this set of equation by setting E change to B, B change to minus E, and then also set J to 0. Okay, J alpha or the 4 vector to 0. Then you get the similar expression. But to do that, you need to introduce tensor that has that kind of property. You cannot just simply do this transformation in this because you don't know whether it's a tensor or not. And so we need to get other tensor from this one. So there are actually two steps to do that. First, you introduce the covariant field vector. Okay, and that actually is the easier part. The covariant ones are just what we define as this F with the subscript alpha beta. And we're doing that using the usual one, using the metric tensor to lower the index. So you use the metric tensor to lower change the subscript to a superscript or vice versa, change a superscript to a subscript. And in this case, it's a tensor, so you need two metric tensor. So you have like multiplied by a covariant matrix, so alpha gamma, G beta delta, and contract the gamma and delta with the field tensor F superscript gamma delta. That's how you do this changing superscript to subscript. Okay, we talk about that. Probably you're not familiar, and in math physics we'll go through it again. But for us, it's easy because this G for special relativity is the Minkowski metric, which is easy. First, you can go through the motion and do the matrix multiplication, because you can write this multiplied by that and multiplied by that. It looks like a multiplication of three matrices. So you can do that. That's not a problem. And the G is simple. For us, it's 1 minus 1. This is a convention used by Jackson. Well, many people do that also. That's one of them, and then you multiply by this F. You multiply by this F down there, and then multiply by the other one, which is also the same. Right? Generally you need to do a transpose, but for us, this is a symmetric matrix, so we don't need to do a transpose. The transpose, when you say transpose exactly the same. You know what I'm saying? The matrix element is this multiplied subject. This is sum over gamma, and delta. Supposedly you need to multiply by the delta should be the front index. But you can reverse this too. The G is symmetric, so you can reverse that. That's fine. Okay. Suppose you can substitute this into this, and then do the multiplication, matrix multiplication. But for this tensor is quite straightforward, because there's 1 in here. So any 4x4 matrix, that the first column is multiplied by first row is multiplied by this first column, second, right? So the first column, so the resulting, this multiplied by that, the column doesn't change, because the first column is multiplied by this. As you say, this is not restricted to FL, but for any of these 4 tensor, it's doing the same thing. But let's just do it explicitly. And then you recognize the pattern. If this is this one, right? Right. So this multiplied by this one multiplied by that one. So you see that the first element is this one multiplied by this one. Obviously, is 0, totally 0. And the second element is this row this row multiplied by the first column, which is obviously just the EX, right? And likewise, the second one, this row multiplied by this column, X, UI, and then the EZ. So basically, the first column doesn't change. And you see that this is not just restricted to this one. Any 4x4 matrix multiplied by this one is keep the first column the same. Okay. Now you do the same thing for this second column. Is the first element, this row multiplied by this one, and basically you just change the sign. So this one multiplied by this one. This the second one, change the sign. So EX minus EX. And this one is this one multiplied by this one, so it's 0. And then this one multiplied by this one, so 5 minus BZ. And then this one multiplied by this one is BY. So B change sign, like BZ changes with this one. And now you can convince yourself that the rest are the same, because it's just different -1 components, but the end result is the same. So all the electric field doesn't change sign, all the magnetic field change sign, and then minus By 0 and Bx and minus Bx 0. Okay. Now one more of this similar thing, but this is actually this one multiplied by that. Actually, that one will keep the first row unchanged. Like we can check that the first row is this one multiplied by this one, right, which is 0, obviously. The second one is this one multiplied by this one is 1, so the first row, the sign doesn't change. Okay. And then the second row is this one multiplied by this one, so you change the sign. So minus X, minus B1, minus EZ. And then also this element obviously is 0. This element, this one multiplied by this one, so this change sign again, so minus BZ. And obviously the other one is the same. B1 change sign, this change sign, 0 minus Bx minus By, Bx 0. The final result is this one. But you compare with the original one, what is actually doing this operation actually is keeping all the magnetic sign of the magnetic field unchanged. So it's the magnetic field components, all the sign are the same, but the electric field change sign. Okay, so electric field change. So this is not just restricted to this field tensor. Any tensor is like that. You do a contraction like that using the Minkowski matrix. Basically, the row first column and the first row doesn't change sign. The rest, I mean, the first row and the first column change sign, but the rest doesn't change sign. It's similar to this one. You change this to like for A, you change to the A subscript. Then the first element unchanged. Then the spatial part change sign. But this is just for the 4 vector. It's like that. For tensor is different. It's the first row and first element that change unchanged. I mean change sign, and then the rest unchanged. So this is slightly different, but then the reason is actually the same. Okay, and these are restricted to Minkowski space. Right? If you have a more compact metric tensor, this obviously doesn't work. Okay, all right. So that's the first introduction. This covariant 4 tensor. But then we have another step, which is even more complicated. And this so-called the dual tensor. Probably need some more space here. I mean, we do a lot of this work so that we can write down these two equations in a more nicer form. The definition of this dual tensor is script F is covariant, a countervariance alpha beta, but there is a contraction with this anti-symmetric epsilon, which is what we call the Levi-Civita symbol, but it's 4-rank tensor. This is an anti-symmetric 4-rank tensor alpha beta gamma delta, and then contract with this the covariant field vector, contract with the gamma delta component. Right, and this looks horrible because they are now into this 4-rank tensor. But this 4-rank tensor is just like the usual epsilon in 3-dimensional space. It's just the what we call the anti-symmetric tensor. So basically, we can define, hopefully still. So alpha beta gamma delta is defined as 1 if alpha beta gamma delta equals 0, 1, 2, 3, and even permutation. So permutation means that you interchange 2 of them. So alpha beta gamma either equals 0, 1, 2, 3, or so it's changing 2 times. You change it 1 time, so 1, 0, 2, 3 is 1 term, and 1, 0, 1, 0, and then you change 0 until 1, 2, 0, 3 is 2 times. Okay, you interchange 2 of them in 1 time or 1 permutation. Interchange it two times and even. Any time you change it, if it's required to change 2 times, then it's keep 1. So it's -1 if odd permutation. If you interchange it just 1 time or 3 times, any odd number is -1. It's 0 if you have repeated index. Repeated indices. Okay, so if 2 of them are the same, then it's 0. Any 2 of them are the same as 0. So this is the same rule as the 3-dimensional epsilon. Okay, and so although it's a 4-rank tensor, but there are lots of 0 in this tensor, and you can check that it's a tensor by the straightforward using this definition and the straightforward definition of a tensor. Convince yourself that this is actually a tensor, or you can do it in a more abstract way to show that it's actually a tensor, right? Now we'll do a contraction of this one. Again, it looks horrible, but I mean, facing with this kind of a looks like a tremendous complexity. All you need to do is just be patient and then do it one at a time, okay? And consider all possibility. Okay, so but I mean, obviously there are very simple cases. This is also anti-symmetric because this is anti-symmetric, and obviously if alpha beta is 0, 0, or 1, 1, or 2, 2, 3, 3, this automatically will kill you, right? Because we said that this repeated index is 0, so this epsilon will kill all the diagonal elements. So, and also by this odd and even, so alpha beta and alpha beta here, you change alpha, interchange this to become beta alpha, interchange this to beta alpha, And according to this, we introduce a minus sign. Okay, so that show that this script F is also anti-symmetric. Okay, so end up this one also only has 6 independent elements. So although that at first looks horrible, that looks at lots of elements to check, but then we get rid of diagonal elements, we get rid of part, the other half of the rest. Only 6 of them are independent. Okay, so we just need to check one at a time. So like F, the script F, say CO1. So you have just like here, you have CO0, CO1, CO2, CO3, and so on. So say FCO1 is, look at this one. Hopefully I get enough time in that. Okay, so now this is already CO1, right? And you need to sum over this gamma delta. But then according to this rule, so there are only 2 possibilities. You fix alpha beta is CO1, then the only possibility is 2, 3, and then 3, 2 that have non-zero, right? There's all other combination of alpha, gamma, delta to be 0, right? CO1, 2, 3, or CO1, C2. Yeah, because of this rule, right? So you only have 2, actually you only have 2, so it's not too bad, right? Now, the CO1, 2, 3, which would be this case, so it's positive, and that would be F2, 3. And then the CO1, 3, 2 will be odd permutation to introduce a negative sign. And this interchange is 3, 2. And now we just look that up. Not this one, because this is subscript. Look up this one. So T23 is CO1, 2, CO1, 2, minus BX. Okay. So minus BX. And 3, 2 is 3, 2 is BX, right? But you have minus sign, so minus BX. So 2 minus BX altogether is just minus BX because you divide it by 2. Okay. That's not too bad. So, right? So this is the CO1 element. Let's check the other one, and you can convince yourself that the CO1, CO2, CO3 are similar considerations. As like CO2 would be By minus By. So this I'll just skip because I'm running out of time. So it's minus By. F CO3 would be minus BC. Just like the same consideration. Okay, we'll change that to B. Change all this to B. Okay, now let's check one more. It's this. This is 1, 0, 1, 2. Let's check 1, 2. Script 1, 2. Script F1, 2. Now the same consideration. If this is 1, 2, then the 3 possibility is 3, 0 or CO3, right? And 3, 0 is positive. 1, 0, 1, 1, 2, 3, 0 is positive. 1, 2, 0, 3 is negative. Okay, and so that is the first positive one is 1, 2, 3, 0 as F3, 0, and then the other one is negative. Okay, and now again look up this one. 3, 0 is this one, so minus EC. Minus EC, and this works out. Minus EC. And CO3, CO1, CO is EC, but the American sign is minus EC, minus EC. The 3 CO is this one, is minus EC, CO3 is this one, easy. So altogether is just minus easy. So 1, 2, 1, 2. So 1, 2 is this one. Instead of BC now, it's minus easy. Did I get it right? Wait. Let's think of that. The script of that script F is 1, 2, 1, 2, 3, 0. 3, 0, 3, 0 is 0, 1, 0, 0, 1, 1, 1. 0, 0, 1, 0, 2, 0, 3, 0. 3, 0 minus easy. Minus easy. Easy. Well, it's 2, 1, 1, 0, 1, 2 minus. It's easy, it's right, but I should get a negative sign. If I do it correctly, I should do all right. I might have to look up I should look up this one. 3, 0, 3, 0 is minus easy, C, 0. Let's see, what did I miss? Yes, this should be easy, right? According to this textbook, alpha beta is this is 0. This one?
No, the F12 isn't F03 one with the plus and F30 is one with negative.
1, 2, 1, 2. Oh yeah, you're right. Yeah. I just lost count of the permutation. Yeah. So you need to start from this. So you need to get to 1, 2, 3, 0. Now how to get this to 1, 2, 3, 2, 0? Permutation. First you interchange this two, become 2, 1, 3, 0. Interchange this two, becomes 3, 1, 2, 0. And then interchange this two, becomes 0, 1, 2, 3. Yeah, 3 of them. So that's negative one. Yeah, you're correct. I lost count of this permutation. Minus is plus. So altogether is plus plus. So this is plus. Okay. So all these things just need to be a little careful. All right. And so that's 1, 2, which is this component. So instead of BC, compare with this ordinary F, this script F is BC becomes easy, minus BC becomes easy. And likewise, you can check that, so F13 will become minus BY. 1, 2 become minus EY. F23, this is 2, 3 component. 2, 3 will becomes EX. So the end result of this script is doing exactly what we want. So it's found a way to. No, we actually this is just the previous one. So yes, so now this is the ordinary field tensor, the field tensor. Now basically just like what we do is changing E to minus, changing E to B, so keeping the sign. Anti-symmetry. And changing B to minus minus E, dz minus E of EZ minus EY and EX. EZ, EY, and minus EX. So that's the script dual tensor. With Jackson. Yeah. That is this operation will do very complicated expression with this fourth rank tensor, but the end result is just like what we try to do. Change the E to B and B to minus E, which is this one. So by this argument, the two source-free Maxwell equation would be just like this one, would be partial over square partial beta, and set the right-hand side to 0. That's the same consideration like what we did here. So, so because this script F satisfies this operation, so you transform this set of Maxwell equations to this set of Maxwell equation. So the corresponding tensor form of the equation will be this one. Okay, is that okay? So now all four Maxwell equations are this one, this one with source with the J on the right hand side, and this one is the script F with the dual tensor. The right hand side is 0. Okay, so now we reduce Maxwell equation to two equations. Except what we usually said is 4 Maxwell equations. Actually, now comes 2. So that is some progress. There's another form in the Jackson 11.143. It's written totally in this covariant field tensor, but the form is slightly more complicated, and they actually express it in a third rank tensor form, although there's lots of symmetry because this F also is antisymmetric. So, but we'll not derive that. To check that, you just again component by component. Instead of using the script F, now you use the covariant F. But doesn't look that nice as this. This way look nicer. Although it's introduced by introducing this object that take a while to check. Okay, so that's all the Maxwell equations. Okay, so I mean it's not easy. Yeah.
Just thinking about because for the comps, right? It's so
yeah.
Like, how am I gonna? What's my workflow?
Yeah. It's
how do I?
If what do I in case people ask you to rederive that, so these are all the steps. And the one thing is just keep cool, calm down, and do it component by component. All this tensor notation, at first you look at that, it looks horrible. Like if you look at all these cosmology paper, I mean, general relativity paper, at first it looks unfamiliar, all these tensor and all that. But once you settle down, it's just a language. You just follow the rule, and to check explicitly or do calculation explicitly, all you do is just index by index, just like the ordinary vector. I mean, you write a form in vector form, but when you do calculation, you just do it component by component, use all the components. And the derivation is similar. This like how you check this, how you get the final form is just how to get the final form. You just check one by one. Although I skip a lot of things, I just check one of them. But if you want to check all of them, just do it explicitly. Now this is in abstract form, right? So alpha beta variables, but to check it, you just put in explicit number. You check it. So instead of alpha beta, you check CO1, CO2, CO3, check all of them, and finally you convince yourself this is the final form. So there's no magic to that. It's just patient and don't panic. Yeah. All right. Then we'll go back a little bit on this section, right? About 5 minutes or so, because we need one more equation. We get all the field equation, the Maxwell equation. We still need to transform the Lorentz force law and writing it in all this tensor notation. We'll do that. So now all these are done. Okay. Yeah, we'll finish. Okay, that's one more note. Is like at first, like what we did previously, the Lorentz force law is written by the fact that the force is the same as for one particle anyway. It's the change of momentum of the particle. dp. P is the usual momentum in Lorentz form is m times v. And the ddt change of time derivative of momentum is the force. So we're writing this as the Lorentz force. And this is in Gaussian, so you have v divided by c. But in SI, you don't have to see. Okay, so now we want to write this in for tensor, also for vector form. And there's one more property that I mentioned in Jackson in this section is the charge invariant. The charge, whatever frame that you measure the charge, given a charge density, and it's the same. It's basically saying that this is a little bit related, but not exactly because we have a charge also, but the charge, if you do a integration of the charge density over the volume element, give you the charge. And what is said is this it's invariant if frame if you do a transformation of frame from K frame to K prime frame or vice versa, these two elements are the same. So the argument of that is that the four elements, obviously the four elements is the same. You have the four vector, right? The fourth element x is equals to the four element of x prime. Right? And the reason of that, this changing x to x prime or x prime to x is basically changing the element multiplied by the determinant of the transformation matrix. In this case, it's partial x prime. This is a tensor, 4x4 matrix, and take the determinant. And for Lorentz transformation, you can convince yourself that this determinant is 1. Okay, that you just do it like the matrix that we always talk about, or in this case, actually maybe in parts. It depends on which way you want to transform. Right, you take the determinant, you can convince yourself this is this one. So gamma times gamma minus gamma beta square, and become gamma square times 1 minus beta square, which is 1. Okay, so you can check that right away. It's 1. So this is just 1. But this one is just dq x times c times dt. And then this is the c dt pi, dq x pi. But the rho is the 0 component of a 4 vector. And likewise, rho pi is the corresponding zero component of all vector. So, and the rest is the spatial part of all vector. So this is analogous to this one. So so this means this equals to this means because they transform the same. That is, this transform like a time element. This transform like times element. So so therefore you have this this statement that the charge is independent of frame is a covariant, or what we call a scalar. Okay, and I mean what we established that by the continuity equation, charge is conserved in the frame, but then we later on also argued that the charge actually not just conserved within one frame, actually the value of the charge is the same in any frame, any Lorentz transform the frame. Okay, so this Q is actually the same in any frame. Okay, and now to transform the equations, and what we need to do is by suggestion instead of dividing it, because we have this momentum for vector. It's this P0, and then the P for a particle, this P0 is just M times U0, which is gamma times C, and then the P in this case is gamma times U. I mean gamma times the non-relativistic U times M. Or in this case, it's actually V. In this case, or in four vector is using U, so M and U0, and then U vector. It's just the same. The U0 is defined as this one. U is defined by this gamma times V. Okay, and now we compare that with this set of equation. We are writing as two equations. So and also we change the ddt. Remember this d tau is dt divided by gamma, right? And so ddt is gamma times d tau is the proper time, the derivative with respect to proper time. So when we write it like here, and so this becomes dp. This is d tau. dt is d tau times gamma, multiply gamma to the other side. This is q. Then you have a gamma, which is just you have just the u0. U0 divided by c. You have u0 e divided by c, and gamma multiplied by this is just u, and then cos b. This is still not in the covariant form. And then this is just the spatial part. The energy part is the conservation energy. This is like the force dot in the velocity is the work done. So it becomes it's E dot in the velocity U, this part. And E dot E. I'm going it maybe a little too quick. But I mean, all these suggestions would be, finally we write that in the form that is combining these two. The form is in equation 11.144. Will be d this p over d tau. Just use this one and this one in the here, And now the last step is just need to be checked explicitly. Right? It's just contraction of this field tensor with this U 4 vector. Like for the 0, 1, basically 0, all this contraction is sum over all this one. This is just like a matrix multiplication. Matrix multiplied by a column vector, this one multiplied by this as a column vector. So basically it's just the spatial part dot into this spatial part U. So basically this one. And the rest is has 2 parts. So like the one part is first you have this EX, right, cut into the 0 part, which is U0, is this one. And then this 2 contract with the corresponding part in the U. That we'll get the X component of U cos B. Okay, so so you can check that. That this is corresponding to this one. Okay, so finally, out of time, so that's why I'm rushing it. Okay, so finally we got everything. We got the source with the Maxwell equation with source, Maxwell equation without source, and the Lorentz force law. All these are now in covariant form. So all the electrodynamics equation now in covariant form. All right. So on Monday we'll finish 11.10 hopefully, and that is actually commonly asked question how you transform the field from one frame to another frame. So we'll get that done on Monday. All right, we'll stop here. Any question before we stop?